Start, please.
Okay. I'd like to talk about first of all about simplicial model categories. And, the first part is simplicial model categories. Let me give the definition. First of all, by functor between model categories is a left equivalent bifunctor if it preserves colimits in those variables and also if the associated push-out product bifunctor, and if this associated push-out bifunctor maps pair of cofibrations to a cofibrations that is a cyclic if and only if either of the domain cofibrations are maps cofibrations to cofibrations and to cofibrations, the pair of cofibrations to cofibration that is acyclic if and only if of the domain are cofibration. Okay, and what is a push-out bifunctor? Push-out bifunctor is given by the Leibniz construction. Consider two variable adjunction. Tensor product, those these coproducts and the home product. And it is called two variable adjunction if we have the following isomorphisms for any objects. So we have the following. I think okay. And if P has a push-outs and N have and Mn have pullbacks, then we can form a two-variable adjunction. Between the categories of arrows, we can consider functors between the working category and the and some category M. This is just arrow category. Okay, and we have the following thing. and similarly for home. Okay. What is a push-out product? Push-out product is a simple thing. We can consider if we have an arrow I from M to M prime in this category, and also we have some J. Then we can form the following diagram. From the tensor product, we can move by means of composition tensorial product I with the identity map to this product, and we can move by means of this arrow to M tensor M prime. And then we can form a push out and the map between and for any such M prime and N prime, we can we have by universal property the following morphism from push out to M prime tensor M prime, and it's called push out product of I and J. Okay, and similarly, we can form a pullback to tensor and home product. If we have an arrow F from P to P prime and arrow I from M to M prime, then we can form a pullback it maps to this one, and we have a following, and we can form a pullback, and this object for this object there is a unique map to the pullback. Okay, and this map is called pullback cotensor. Okay, and I won't give the similar definition for home product, but I'll give the following example, simple example. If we take the first arrow as a first arrow, the following map from initial object to M, and for J we take the following arrow, then the push out product is just a morphism, from M tensor N to M tensor N prime. Okay, and there is a simple proposition which says that if we have some classes A, B, and C maps in the categories M and P, specifically, then the following lifting properties are equivalent. This one is equivalent to this one. Sorry, this one is equivalent to this one, and also is equivalent to this problem, this lifting problem. Okay. Now I wanna prove the following proposition. Left equivalent by functors are homotopical on the subcategory of cofibrillant objects. I also preserve cofibrillant objects are homotopical on the subcategory of cofibrillant objects and preserve cofibrillant objects also. Okay, proof. Let's prove this proposition. Suppose that we have two weak equivalences between M and M prime and N and N prime, and we should prove that the following push-out product is also weak equivalence. This is a weak equivalence, and we want to prove that this is also weak equivalence. For doing that, we should decompose this arrow as in the following manner. Firstly, we can to obtain the map I tensor J, we firstly apply the map I tensor identity, and then we will obtain M prime tensor M, and after that we apply identity tensor J, and hence we have the following decomposition. But each of each of this arrow is a weak equivalence. It follows from the previous example. It follows from this example because we know that this map is a co-fibration because we know that M is a cofibrant, and then the push out of this map is also cofibration. This map is a push out. This map is a push out. Full push out. Okay. Then if I is a trivial cofibration, then push out of it push out of I is weak equivalence also. Okay, and similarly, we can prove that this one is a weak equivalence. Similar, yeah, and thus the composition is a weak equivalence, and we're done. Now, let me formulate the following proposition. If we have a tensor, cotensor, and Hom is a two-variable junction, then this tensor product is a left Quillen junction if and only if is a left Quillen junction if and only if this coproduct is a right Quillen junction, and if and only if Hom is a right Quillen junction. Okay, it follows immediately from the Leibniz construction and also from the previous property of the Leibniz construction from this proposition. Okay. Now I can give the following definition of a simplicial model category. Simplicial model category is a model category that is tensored, cotensored, simplicially enriched, and such that the two-variable adjunction is a Quillen two-variable adjunction. Now I discuss final functors in enriched categories. Final functors in unenriched categories. First of all, I want to give the following easy lemma, but this lemma clarifies the definition of the homotopy, terminal functors, and it motivates it. If suppose that D has a suppose that D has a terminal object. Say T, and we have a, and for any functor f from D to M, we have that colimit of this functor, or D, is just is isomorphic to f of T. Prove this easy lemma. Consider a cocon over X. And by definition of this cocon, there exists a map, say tau from ft to x, by definition of cocon. For any arrow from D1 to D2, we have the following diagram. And also for any cocon under X, we have this map. This map tau. And in particular, we can take ft and ft, and then we will have that there is a we will have the following diagram, and from this diagram we can see that from commutativity of this triangle, we have that this tau is unique, the unique map. So suppose that there is another map rho, then from commutativity we will obtain that this rho just tau. Okay. Now I give the following definition of the what is a final functor? A functor k from the category C to the category D is final if for any diagram F from D to M, we have the following isomorphism between co-limits of the composition F and K with the co-limit of F over D. And dually, we say that K is an initial if for any diagram F, we have isomorphism between limits. Okay, let me give the following example. The functor, we can form the functor if we have the category with a terminal object, we can form the following functor from the category with one object and one morphism to the category, to some category, and where image is a terminal object. Then this functor is final. It proves the previous lemma. Okay, now we want to characterize when the functor is final, and it can be done by means of the characterization of the slice category or comma category over functor. And the functor K is final if and only if for any D the slice category is non-empty and connected. We will use this lemma later, but firstly, I recall what is a connected category and recall this definition. Connected means that any pair of objects can be joined by zigzag, finite, of course, and we can also define if we have two objects, if we have some zigzag, then for any two objects, then we say that this category is connected. Okay, and also recall what is a functor pi 0. Pi 0 is a functor from the category of small categories to the set, and it sends the category to its collection of objects up to zigzags. Okay, and now we can prove this lemma. Prove this application. First of all, if we are given a functor f, then con under f obviously produces con over f over this composition, but converse is also true. Say if we have a if we have some con under f under composition f and k to m, then there exists an arrow from D to kc as the category D over k is connected, is non-empty and connected. Okay, then we can apply the functor f to this map, and we can take after that the composition with the lambda c. Then we will have the following composition: fd to fkc, and after that fkc to m. Okay, and we have a cocon from fd to m. And it's easy to see that that if we have two variants of this cocon, then there is the following commutative diagram, and it means that the set of the set of cocons under Fk and under F are isomorphic. This diagram means that the set of all cones under F is the same as a cocon under Fk is isomorphic to the one of to the one for the functor F. Okay. Thus, if we have an isomorphism between these sets, then we have an isomorphism between the colimits. Another implication note that for any diagram X from C to Z, we have that pi 0 of the category of elements is isomorphic to co-limit of X over C. What is the category of elements? Recall that this is a category with objects are pairs Cx, such that C is the object of C and X is from X over C, and the morphisms just arrows between C and C prime, such that X of U of X equals X prime. Okay, and then from the definition of the category of elements, we can derive that there is the following isomorphism. And now, pi 0 of this category is just pi 0 of the category of elements. As we have an isomorphism between these categories. We know that category of elements. We know that category of elements over the functor, which is like this, is the same as just slice category. It is an exercise. Okay, and also we know that this is a co-limit with C of this functor, but we suppose that K is final, and then we have the isomorphism. This is just a composition of the functor, the following functor, and the functor k. And then we have isomorphism, but this is just a point in the set. Thus, we have that pi 0 of this slice category is just one element set, and hence this category is non-empty and connected. And we're done. Okay. Now we have the following corollary. For any cat, the co-limit of the identity functor is just a terminal object, and also conversely for any terminal object, any terminal object defines a co-limit. We can prove, of course, we can prove this fact without the following technique, but now it's very easy. Suppose that T is a terminal object for D. Then we have a functor, and this functor is final, and it implies that co-limit of this functor is a co-limit over composition of functors. But this composition is just T, and then we have that we get the desired isomorphism. Another implication is left as an exercise. Yeah. Okay. Now we can discuss the following the next chapter. This is a homotopy final functors. Homotopy final functors. The previous section was a motivation of the following section. Definition: a functor k is a homotopy final if this nerve is contractible. For all D from D, and it's a homotopy initial if it is a homotopy initial if the nerve of K or D is contractible. Okay. Now I'll give the following famous lemma, famous easy lemma. If D has a initial or terminal object, then it implies that the nerve of this category is contractible. The proof is very easy. If D has a terminal, we prove that for the terminal object, and in the same way we can do this for a terminal object. Okay, and if D has an initial object, then we have natural transformation between the following functors. The first one is just a constant functor on initial object, and the second one is just identity functor. But we know that if we have if you have a natural transformation between functors, its natural transformation defines homotopy between nerves of corresponding categories. If we have a natural transformation between functors f and g, f from C to D, and also G, then it defines. Oh, sorry. We can build the following functor, where this one is a working category, and after applying the nerve and using the fact that nerve of the product is the product of nerves, then we have the following homotopy. And it will give a homotopy, and thus we have a contraction. We have a contraction homotopy. We have a contraction homotopy. Okay. Now we are interested in the situation when the functor is a homotopy final. What is a characterization of such functors? For giving this characterization, we need the definition. A category C is filtered if in this category for any diagram there is a co-cons. G is filter if for any diagram there exists a cone of this diagram. And the following lemma gives a characterization. If K is a homotopy final, then K is final. But and also conversely, it's true with if we additionally suppose that the category C is a filtered category. Conversely, if C is filtered, and K is final, then K is homotopy final. Proof. Firstly, we'll prove the first implication. For any category, we can notice that there is a isomorphism between the pi zeros. Okay, and if K is a homotopy final, then of course the nerve of the slice category is contracted. But it means that pi zero of this slice category is just pi zero of the nerve of this category, and just a 1-point set. Thus, d over k is non-empty and connected by previous lemma. Conversely, suppose that the functor k is final. Hence, the category d over k the category d over k is filtered if the category is C. So this is an exercise. And also we use the following fact that nerve for filtered categories is contractible. It can be proven by means of X functor, but I'll omit this proof. Use the classical result that nerve of filtered categories is contractible. And we're done. So the following theorem motivates the definition of homotopy final functors. Theorem motivation homotopy finality theorem or motivation for homotopy and final functors. Suppose that F is a sum diagram in simplicial model category. If K is a homotopy final, then we have that homotopical limit of the composition F with K over C is isomorphic to homotopical limit of F over D. Okay. And now we prove this important theorem. But okay, we prove, and after that I'll give some examples of its application. If F is a homotopy final, then we can notice that we have the following weak equivalence. We have this weak equivalence. The first term is weakly equivalent to points by definition of a homotopy final functor. And the second one is equivalent to point because we know that this category has a initial object, and then the nerve is contractible. Okay, and also we know that the nerve this construction is this functor, the weakly equivalent is isomorphic, sorry, to the following bar construction. Also, we know that this one is isomorphic to this bar construction. Where it means that we have here the following functor. We omit this functor in this, and okay. And the third fact is that this functor preserves weak equivalences. Thus, using these facts, we can form the following diagram, and this diagram will prove the theorem. It looks like proof of the theorem in the previous talk. We have the following giant diagram. It maps to this bar construction, and what is a map? What is a map? This map is just is induced by the map from this one to this one, but this term is equivalent to this functor, and this term is equivalent to this functor. But between these functors, there is a weak equivalence, and we know that this functor preserves the weak equivalence. Then so we can apply the letter one and to these objects, and after that we will obtain the weak equivalence. Okay, Now we can replace this this guy by this guy, and we use a associativity property of the bar construction. We move this bar construction. We change the order of the brackets. We use just associativity of the bar construction. It's some property of bar construction. Okay, and it maps to this bar construction. And here we have also this map by the associativity too. And the second vertical map on the left is just to the bar construction, the following bar construction. What is a map? This map is induced by natural augmentation. We have the following natural augmentation or contraction. We can give their contraction homotopes, and this contraction homotopes give the weak equivalence. This weak equivalence. The first one, the second one is on the right. Okay, and after that we can map to homotopical limit of composition and homotopical limit of F. And here we have an isomorphisms by definition of homotopical limit. We know that these things are equivalent, and also in this case. Okay, thus we have these weak equivalences on the left, weak equivalences on the right, vertical maps, and also horizontal weak equivalence. And by 2 of 3 property, we will obtain that the bottom arrow is also weak equivalence. Okay, but conversely, it's true that if for any functor f we have weak equivalence between these Hoko limbs, then we have the fact that k is a homotopifinal functor. It's an easy consequence of this diagram, because if we know that we have this isomorphism, then also by 2 of 3 property, we will obtain that this map is also weak equivalence. But we know that this one is just a point. Oh, sorry, just a point. And it is just north of this thing. Okay, and thus K is a homotopy final functor, because we have an weak equivalence between this nerve and the point. Okay. Now we can prove the corollary. It's a equivalence theorem A. If K from C to D is a homotopy final, then we have a weak equivalence between nerves. It's an easy corollary. We know that geometric realization of the nerve is just a bar construction like this. And it is also a homotopical limit of the constant functor over C. But we can decompose the map from, we can decompose this functor into composition of two functors. The first one is a functor K from C to D, and the second is just a constant functor, and it's just a composition of a constant functor and functor K. And there is a map from this cocolim to this one. But we know that K is a homotopy final, then we have a weak equivalence. Then we have a weak equivalence by the previous theorem. And thus we're done. Okay, consider the following example. Suppose that category D has a terminal object T. Then the functor T from, we know that this functor from the one object category to D is final. And also, of course, one object category is filtered, and thus T is a homotopy final. Hence, we have an isomorphism. And then, in particular, if we consider the functor between working category and category D, some functor F, suppose that f of 1, f of 0 is x, and f of 1 is y, and f of the arrow as this arrow from X to Y, then homotopical limit of the F along working category is just Y or cylinder of F, or the map F. Okay, the next example. We can consider the category subcategory with only monomorphisms, subcategory of ordinal category with only monomorphisms, and this inclusion functor is a homotopy initial. We should prove that the slice categories, such as M over N is contractible for all M. Okay, and for doing that, we can construct the end functor S, which sends the map from K to N, which is an object of this slice category, to the S of alpha which is defined in the following way. S alpha of 0 is supposed to be 0, and S alpha of I is just alpha of I minus 1 when I is greater than 0. Okay, and also we can consider the following stupid functor. Is a constant functor on the object, on the 0 object. And one can verify that we have natural transformations from identity functor to the functor S, and also we have a natural transformation from this not interesting functor, and thus we have a, if I take a nerve, we have a zigzag which and then we have that this nerve is contractible. Apply nerve construction, and we discovered that if we have a natural transformation, then it converts to homotopy after applying the nerve functor, and thus this nerve category is contractible by means of this contraction homotopies. Thus, homotopy co-limit of the simplicial object over usual category delta is isomorphic to a weakly equivalent to the 1 over over this category with monomorphisms. Okay, and also in this context, there is a construction of so-called fat generalization, fat realization. Fat realization. Fat realization is just we can form the following Kahn extension, left Kahn extension. We can map this category to the category of simplicial set, but this category can be embedded into simplicial sets, and after that we can form the left Kahn extension. And if we use this Kahn extension in the usual definition of the realization, which are given by the Cohen formula, then we have a so-called fat geometric realization. Okay. I'll give the following example. If delta is a diagonal embedding, then it is a homotopy initial. It can be proven as in this example. We should construct the end functor, and after that some contraction homotopies, and by means of constructing the natural transformations. But I think I can left it can be left, and I formulate just a consequence of this this observation. Consequence is that homotopical limit of x, where x is a bisimplicial set, is a weakly equivalent to homotopical limit of its diagonal. Okay. And now I suppose that I should give an example of computing the homotopical limit by bar construction. I'll give the explicit computation. This is another computation for the homotopical limit of usual map, and we will obtain in the other direction the cylinder of a map. If we have a functor from the working category to the topological spaces, then north of working category is one skeletal. It means that only one skeleton generates simplices, different simplices. So the bar construction, bar complex. So bar construction is one skeletal tool, and thus we can consider only the one simplices or zero simplices, and because we will form the realization of this simplicial object and simplicial space and simplicial object, and we can consider thus only the one skeleton. Okay, and B0 is just this coproduct of some x and y, where suppose that f maps x to y. Okay, and B1 just the following thing. Any term any term corresponds to the arrow in the category on the working category. So yeah, on the working category. It corresponds to the identity map from 0 to 0, and this corresponds to the map from 0 to 1, and it corresponds to the identity arrow 1 to 1. Okay, thus, but we know that homotopical limit of the functor f can be computed as a geometric realization of the bar complex, but it is the same as this tensor product. And also it is a coherent. But this coherent can be computed by co-equalizer. We can form the coproduct along arrows from M to N in the category delta. And it maps to the such a product, and explicitly we can write this term as a colimit of the following diagram. We should consider all variants of choosing M and N. If M equals 1, then we have delta 1, and if N equals 0, be 0, and so on. And now we should draw some arrows. If we have an arrow from 1 to 0, then it corresponds to the map from delta 1 to delta 0, because delta is a covariant functor, and it is just S0 And also F gives the morphism between B0 and B1. Recall that this functor is a contravariant functor, and thus we have a S sub 0 arrow. Also, we have the arrow from 0 to 1, and it corresponds to the following arrow, and of course, but there is a there are two morphisms, and each morphism will give a Z0 or Z1, and also and it's the same with the subscript. Okay, thus we should draw the following arrows. The first one is from is the same, is the following arrow. This is okay. I just draw the arrows, and I won't give a comments. Give comments. Yeah, and it can be verified that the letter diagram, the letter colimit, is just a usual cylinder. Okay, but thus we have the second approach to obtain the colimit of this functor. But there is a more general approach which uses the ready model category, and I suppose that I'll give the one in the next talk. And okay, and I think that we have no time, and this is all what I want to talk about.